Won't we get the E naught in negative?
हो सकता है. Yeah, why not? Right minus left, right? So copper का जो भी है, so copper is 0.34 minus negative नहीं आ रहा है, minus of minus हो रहा है ना?
Understood.
But even if you get negative, like there's no rule that it should be positive. Like if you're doing it in a real life thing, then you need to care about whether it's positive or negative. But it all depends on what materials you're taking, what their E naught values are. So. Send your answers over chat. Right back. And send it properly with units. Okay, Kaveri's already sent it. Sia also sent it. Oof, I want to see her calculation because very close values, but different. Smera got same as Kaveri. Was there any sort of division that you had to do, any rounding off or something, or was it straightforward?
There was 0.059 by 91 by 2.
Okay, by 2 is pretty straightforward. 0.059 or 591. Same difference. Like round off to 2 decimal, then you get 59. See, I check your calculation because given answer is closer to what these guys got versus. You're off by 0.3 units. So
I checked. I divided 0.059 by 2. Then I subtracted 3 minus that.
How 3?
Oh, sorry. Yeah,
0.7. That's why you're
yeah, I
off.
got.
Arya also got it. Okay, cool. Yeah, pretty direct. He has got the hang of this thing. Okay. Okay. The next part. Okay. So that was Nernst equation, like the most basic form of the equation. You can use it to calculate. It's basically the relation between cell potential and concentration. So if you know how much, what is the concentration of the solutions you've taken, you can use that to calculate, okay, kitna aa raha hai cell potential uske saath. Or if you have an unknown solution, you can measure it through the voltmeter and then try and figure out the concentration of that solution. Either way. Now, what happens at equilibrium? Equilibrium means I'm talking about A plus B gives C plus D, right? This is the equation we considered, Nernst equation mein. So when forward reaction is equal to the rate of backward reaction, both of them are proceeding at equal rate. So what happens when this achieves equilibrium? Or
As in?
what happens to the EMF at equilibrium?
Remains constant. Remains the same.
Think about it. So like forward reaction mein, one
Why
of,
would the EMF change in the first place?
think about it. Forward reaction mein, one of them is getting oxidized and the other is getting reduced, right? ऐसे oxidation चल रहा है, and okay, B to D, let's say oxidation is happening, A to C, reduction is happening. So transfer of electrons is B is losing electrons, and as that happens, C is gaining electrons. Like A is gaining electrons to form C.
I'm sorry to disturb, but I did 3.7 and I'm getting like a completely different answer.
2.7, not 3.7. You're saying you subtracted, na? 2.7 minus.
Oh, never mind.
Look at it later, Zia. Like focus on this now. Like maths, like as long as you applied the formula correctly, you added, subtracted the correct values to add, subtract, should be okay. Because signs are pretty important in this reduction oxidation scale here. Okay. All right. So coming back to this, B to D oxidation ho raha hai, A to C reduction ho raha hai, which means as B is losing electrons, A is gaining electrons. So that's the circle of electrons going on, right? What happens in the reverse reaction? If I suddenly, like, when enough of C and D are produced, it's a natural thing. Reverse reaction kicks into gear and eventually this reaction will reach equilibrium. So reverse reaction mein kya hoga? What happens when D gets converted to B?
It'll get reduced.
So then what happens to the direction of electrons?
Ulta.
Ulta ho jayega na? So when the rate of forward and the rate of backward reactions is the same, whatever electrons are being pushed in one direction, the same thing is being pushed in the other direction also.
So there's no N.
There's no what?
There's no N then.
हाँ तो EMF क्या होगा? In that
Zero.
zero.
No.
Yeah, that is correct. So as long as the reaction is being pushed in one direction, you start seeing the EMF because that's literally like flowing of current. That's where that voltage is coming from. But
what
But EMF का definition ही है कि there is the potential of the cell when the current is not present. That's what EMF means.
no, EMF is electromotive force. It is the force that causes
Yeah, but
electrons to flow, to move.
But she's right, no? Like when there is no current flowing through it, that is the what we count as the potential of the cell, no? EMF. So how can it be zero?
Guys, like again, when we done Daniel cell also, like you start seeing things on the voltmeter only when the circuit is complete, only when current is allowed to flow. Otherwise,
But the
is
cell
EMF
be having some EMF, no? Like
Huh?
with or without it being connected in a circuit, the cell in itself would be having some EMF.
is EMF used in electric circuit the same as the EMF we're talking about
Yeah.
here?
I don't know how you like what you studied in electric circuit, but like going by the definition, if you look at the literal full form of EMF, it is electromotive force. So it
Oh,
is
so what you're saying is, see, but what we are talking about is when in electric circuit, that time when you have a particular battery, there is EMF in that, and that is defined as whatever potential that the cell has when the circuit is off, like there's no current flowing through. So whatever potential is present in the cell, that is electromotive force.
so you
So
say once the
in
circuit
that,
is connected, the EMF changes.
No, it remains the same, but we add on to it from the
add
like.
on to the terminal voltage, yeah. Yeah.
So you add EMF plus what?
No, we don't add, I mean, EMF is used to in like to find the maybe the resistance or the internal resistance or the terminal voltage. We're not adding it per se, but the EMF
This is when you turn
the EMF remains the same with or without the I mean the cell in itself would be having certain EMF, and then connecting it to a circuit there would be terminal voltage because on both ends because of the
as
circuit.
well, which
EMF
gets added on.
Yeah.
Okay, so the EMF you're talking about that is contained in the battery, like of course a battery will have EMF because it is prepared in such a way, like that is to be used whenever you complete the circuit. If
It's
you
like we're just
complete the
two
circuit,
electrodes.
huh?
This is not like a proper battery we're using. This is like
No.
two electrodes. Yeah.
Yeah. So yeah, but EMF by itself, like it means electromotive force. It's like the potential that is created that causes the electrons to flow. It's a force which pushes the electrons to flow, and that flow of electrons is the electric current that happens. Okay, so when the electrons face force from forward direction as well as backward direction, basically kind of cancels out, and at equilibrium EMF of the cell becomes zero. Like practically speaking, if this reaction reaches equilibrium, and that at that point if you connect a voltmeter to see what the potential is, it's going to give you a zero reading. Similar situation as yesterday's class, we said, okay, if we connect external what do you call it, an external battery in the opposing direction, if it is exceeding the iska this thing, or if it is equal and opposite to this thing, you said it becomes zero, right? Except in this case, the backward reaction is acting like that. It's like equal and opposite to the EMF of the cell. So overall becomes zero. So this is our old friend equilibrium we're talking about. Do you remember the equation at equilibrium that we studied pehle? Do you guys remember the expression for equilibrium constant? Kc equal to
C
Something
raised to
products
C.
by reactant.
That one, no? C raised to C. D,
Oh,
into
that. Yeah.
Yeah.
Products by
on
reactants,
A.
right? Concentration of
Yeah,
raised to their
concentration of-
stoichiometric.
yes, concentration of reactants. It's literally this thing. Okay.
It was like KSP, no?
KSP is the solubility product. It is the equilibrium constant, specifically when a salt is
Oh,
being.
yeah. Got it.
So this is for any reaction like Kc, because we're using concentration as opposed to Kp. All right. So now let's apply this to Nernst equation. So Nernst equation say we know that E cell equal to E naught of that same cell minus RT by NF natural log of concentration of products upon concentration of the reactants. So let's apply, because we are considering at equilibrium specifically. So at equilibrium, E cell is zero. So we just established that will be equal to E naught of the cell minus RT by NF natural log. Now this whole thing is equal to the equilibrium constant on Kc. So rearrange this a little bit. You get E naught cell equal to RT by NF ln Kc, or specifically at 298 Kelvin or different temperatures, let's say. Another way of representing it, E naught cell equal to 2.303 RT by NF log Kc. So this is establishing a relation between the cell potential and equilibrium constant. So if you want to figure out the equilibrium constant of like certain reactions, because it's like, I mean, equilibrium constant is a constant specific to certain reactions, and you can apply it in a lot of different cases criteria. So if you, and like cell potential is a very real value that you can calculate practically also. Or if you have the standard electrode potentials, you can use that, put it in this formula, and like that's one way of calculating equilibrium constant.
This is not derived from Nernst equation. This is alag.
This is derived from Nernst equation. No, what is this?
Oh yeah. Huh.
So Nernst equation, again, specifically, that's why at equilibrium, we know that physically some things are true at equilibrium, like EMF becomes 0, so we substituted that value. And
Oh yeah.
the ratio is equal to the equilibrium constant because rate of reaction is equal and that whole deal. So we just substituted the values and like rearranged it a bit, that's it. And this is just different variations of it, like natural logarithm converted to this. You can get more variations by putting the values of R and F and T and all of that. Okay, so this is like an
The one that you written in blue is
because this is the expression, this is the derivation part of it. This is the formula that you'll be using. So they've like kind of highlight this part.
At equilibrium, the only the thing is that the electrons are not being transferred because the rate of forward reaction is the same as the rate of backward reaction. So what will N be in that case? Like, how did we come to the conclusion that the EMF is 0?
So electrons not being transferred doesn't mean that they're going to be static and reaction will not happen. Equilibrium is dynamic. It's dynamic equilibrium always. So electrons will be transferred, just that the net will be 0 because whatever is happening in one direction is being opposed, like equal and opposite in the other direction. So
But that is only in reference to the number of electrons. Everything else will still continue to happen, no?
What do you mean everything
The
else?
standard, like the standard potential, the electrode wala thing, and the concentration of the reactants and the concentration of the products, all that is the same. The only difference of a reaction in equilibrium versus a normal reaction is that the number of electrons in this case is we don't really need to consider because the forward is the same as backward. Everything else is the same.
Consider. See, number of electrons is the number of electrons that this is the number of electrons that is exchanged during redox. How much is being gained, or which is obviously also equal to being lost. Yeah, so it'll remain the same. Like this particular A, B, C, D ke beech mein, if 2 plus is getting converted to plus or 3 plus getting converted to 2 plus, jo bhi hai, the number of electrons that are being exchanged in this process. Okay. Again, like finish noting this. Again, like this whole section is going to be very, very numerical. Okay, what happens in this case? What happens in this case? It's just going to be like that. Once you guys are done, we will do another question.
How did we get 0.059 in the previous one and 2.303 in this one?
0.059 is r t equal to 298.
Multiply that by 2.303.
2.303 is simply the natural logarithm to logarithm ka conversion. I have not changed r, t, and f. So
I got that, but 2.303 is a part of the 0.059, or
Huh.
we multiply that.
no, it's part of that.
And once we multiply 2.303 and R and T, we'll get 0.05.
Yeah.
Done.
Okay. Looking for a question based on equilibrium constant. Max function. Okay. Simple stuff. Everybody done? Sia?
Yes, ma'am.
Look at question 28. Ignore this part. So like we'll look at this in the next section. Abhi ke liye just calculate log cases. You don't have to worry about logarithm because you're outright asked to calculate log cases. Leave it. You're given E naught cell directly. This is a very direct question. See if we can finish it in like. Abhi kitna? 445 ho raha hai na? Finish it by 447. See if you can do it. Smira, you attempting this?
Yes, ma'am.
Okay.
They didn't really have to give F, right? If we use the other formula.
Yeah. Yeah. If you know the value 0.059 and what it is, you can directly use that. Yeah.
What will be N, 2 or 3?
Now, N in this case is going to be, acha, ye wala reaction dekh rahe hai na? Is the same thing here either way. Number of electrons exchange. So overall, kitne electrons exchange ho rahe hain yahan pe?
Like net, so 3
Six.
minus.
No. You don't calculate it in terms of net. So,
6, right?
so you need to consider reduction half and oxidation half. Reduction half, oxidation half balance karne mein, like overall, like if you want 1 unit of this reaction to take place, like how many electrons ka exchange need to happen in order to for that to happen.
But the electron flow in case of Daniel cell is only from one of the electrodes to the other, right? So how both of them will have charge?
No, both of them will see, like again, don't take it very, so think about it practically. If you want that cell to work, you can't have only one half of the cell and expect it to happen. Like you need both the reduction half and the oxidation half in order to complete the cell. So uske basis mein, in order to complete this reaction, how many electrons does chromium have to lose? And in the process, how many electrons is cadmium gaining?
But when we say reduction oxidation, उसमें जो oxidize हो रहा है, that is going to lose n number of electrons, and the same n number of electrons the other one is going to gain. That's how the reduction will happen. So why are there two different values?
So that is why you don't take two different values. That's why you end up balancing the equation, right? So in the balanced equation, how many electrons is chromium losing and how many electrons is cadmium gaining?
Chromium is losing 3 and cadmium is gaining.
In the balanced equation.
How do you balance it?
It's already balanced for you. Each atom of chromium is losing 3, but in order to completely oxidize cadmium, chromium needs to lose overall 6 electrons, na? Like 2 atoms of chromium need to lose 6 electrons. Or if you take it the other way around, cadmium is gaining 2 electrons individually.
Yeah.
But chromium is capable of losing 3. Like where will that extra electron go? So in order to balance it, like overall cadmium is gaining 6.
So shouldn't it just be 1? Like, I mean.
No, 6 electrons. Like balanced equation में कितने electrons का exchange हो रहा है? How many electrons are being exchanged in the balanced equation? Try to split this equation into reduction half and oxidation half. Reduction half,
Like 3 to 2, like 3 of cadmium into the 2 plus like that.
yeah.
Oh, acha. Okay. But
Do we have to leave it?
I understood how we got 6. But then why would the value be different in the first place? Because one of them will lose X number of electrons, the other will gain. That's how the whole system works. But so then why would it be two different values? I still didn't get that.
Because the nature of this thing, like suppose redox pair may, if you took sodium and what is capable?
Oh, so it's like not necessary that जितने वो lose करता है उतने ही दूसरा.
Like that depends on the capabilities of
Yeah.
individual metals. Yeah. Okay, Arya,
Do we have to leave it in anti-log?
no, what is log Kc equal to? So just give that one number.
Oh, okay. Oh, yeah.
Arya, Smera, both of you got it. Like you got the same answer. Let me compare it. Question number 28, hai na? 28, kidhar hai? Oh yeah, you guys got it. Sahi hai.
How do we know? Oh, no. How do we know E cell?
It's given there, no?
Where?
Achha, why do you need E cell?
Won't you use Oh yeah, it'll be 0.
You don't even have to go that far. Like that's the reason we do all these derivations. Just use the relation that connects Kc and E naught directly.
Is mine right?
You also sent in, huh? Sahi hai.
No units, right?
No units because this is logarithm of this. So E naught 0.34 will be equal to RT by NF, like all of that we said 0.059 by 6 log Kc. They just have to do this. Kaveri also got it. Awesome. Everybody got it. You just like once you know what values to apply where, it's just simple multiplication division. Check. Cool. क्या है next? Kc हो गया. हाँ. You can also use this like once you have the relation of the cell potential with Kc, you can also extend this to Gibbs energy. Actually, this is the derivation behind the relation between Kc and Gibbs energy. Do you guys remember this? It was like a chotu, really small part when you were studying Gibbs energy. Do you remember the relation between equilibrium constant and Gibbs energy? Gibbs energy equal to, so delta G equal to
Kc and RT log, I don't know,
Yeah.
2.303 log something.
Yes, that whole thing. So if you don't remember it, no problem, because we're going to basically derive it again. All right. So when we're talking about cell electrode potential and all, going back to basics, like in this case, the chemical reaction, the chemical energy, which is the energy between the bonds, like as the bonds break and bonds are formed, the chemical, that kind of energy is being converted into electrical energy, which is like pushing the electrons, flow of electrons, right? So if it's happening in one beaker, like you can't do anything with that flow of electrons, it's happening within that beaker itself. But when you separate it out into separate electrodes and put a connecting wire, you're able to harness it. It's the whole thing with the cell. Which means the electrical work done by the cell, like whatever electrical work is being done by the cell, that's the electrical energy, should correspond to, so that will be equal to the decrease in free energy. Free energy, like talking about Gibbs free energy. Does this make sense? You getting it? No? Okay, so what is the condition like in terms of Gibbs free energy? Like delta G kya hona chahiye in order for a reaction to occur? Like spontaneously on its own. Delta G ka value.
Positive.
Huh?
Sorry, negative. If it's negative, it's spontaneous. Positive, not.
So delta G should be less than 0. So negative value matlab there is an overall decrease in Gibbs free energy. According to conservation of energy, if there is a decrease in energy, it's not vanishing anywhere. It needs to be converted to something else. So in this case, it is being converted into electrical energy, the electrical work done by the cell. like the energy used in pushing the electrons from one electrode to another. Yeah. Now, is it making sense?
I don't get how that would like electrical work would lead to an decrease in it, like Gibbs free energy.
Lead to nahi. I wrote it wrong. It should be the other way around. Like both of them are happening simultaneously because the reaction is occurring. Electricity is happening, right? Like
Yeah,
as
but
the reaction is not happening, the electricity is also not happening. Like when you break the circuit. Yeah.
and as in with decrease in Gibbs free energy, there is decrease in electrical work done by increase, right?
Increase. Yeah.
So, but for a particular reaction, Gibbs free energy value is constant, right?
That constant value is a negative value, right?
Yeah, but how would it lead to, like, it's already a negative. It doesn't mean that the value is decreasing, right?
No, that negative value indicates that it's decreasing. Like that value only we are equating to electrical work done by the cell. See, in combustion
So,
reaction, that energy is converted into heat and light. That see, it's the heat energy, light energy, all of that. In this case, it is converted to electrical energy, the flow of electrons, the current that's happening.
so like, do you mean that the lower the Gibbs free energy for a particular reaction, the lesser more electrical work done by the cell? Because
No.
for one particular reaction, the Gibbs free energy would be constant, right?
Yeah, and that's why for that particular cell, the standard electrode potential also will be constant. It will only have the same amount of voltage being produced.
Yeah, so how is that leading to an increase in the electrical work done?
We're just connecting both the things that are happening. Like, okay, electricity, like if there's a potential, like if that reaction happening is causing the current to flow, it means that, okay, like where is that electrical energy coming from? Like you learned conservation of energy, like energy can't be created or destroyed. It has to be converted from one form to another. So where is this electrical work coming from? It is the result of the change in Gibbs energy that's happening due to the reaction.